Hello and welcome back to math class in session. Continuing, let's do derivatives of trig functions. Derivatives of y equals sine x and y equals cos x. Let's take a look at a sine x function. This is sine x. Well, actually it's 4 sine x because you can see the amplitude is 4 here. But it serves as an illustration. The red line is the tangent to the curve at the point P. Now we can move this point P along the curve, and let's observe what happens to the slope of that red line, the slope of the tangent to the curve. It looks like it reaches 1, and then 0, and then -1, and then 0, and then 1, and then 0, and then -1, and then 0, and so on. And so the derivative of y equals sine x is a function that oscillates between the ones. It goes to 1, then 0, then -1, and then 0, and we know what function oscillates between the ones. There's a function that oscillates between the ones, closely related to sine x, and that's cos x. So the derivative of sine x is cos x. One has to know this. D sine x by dx equals cos x. Meanwhile, d cos x by dx is equal to the negative of sine x. So write those down and remember them. Derivative of sine is cos. Derivative of cos is negative sine. Let's practice. Let's differentiate y equals sine of 5x. 5x in this context has got a name. It's called the argument. It's the answer to the question, sine of what? Oh, sine of 5x. Okay. So 5x is the argument. And to differentiate a function like this, one has to differentiate with respect to the argument multiplied by the derivative of the argument. So this one will be cos of 5x times 5. And we can tidy up this 5 by putting it up front so that it doesn't get confused with the argument. Let's differentiate x cos 3x. Well, this is a product of functions of x. 3x is an argument here. It's the argument of cosine. It's answering the question, cos of what? Oh, cos of 3x. So 3x is not a factor. 3x is an argument. However, x is a factor, so this is a product rule. To differentiate, we'll have to go first thing prime, etc. So first thing prime will be 1 times the second thing plus. The second thing prime will be negative sine of the argument times 3. So it'll be -3 sine 3x times the first thing x. And we can tidy this up by saying minus 3x sine 3x. Notice how the argument stays consistent throughout this question. The original function had an argument of 3x, and the derivative has an argument of 3x in each of the trig functions. Let's differentiate cos of x squared. So it's the x that's squared, and so we'll differentiate with respect to the argument times the derivative of the argument. So it will be minus sine of the same argument times the derivative of the argument 2x. And this tidies up to this. Now, I've deliberately put this next example right beside it, y equals cos squared of x, which is fundamentally different from cos of x squared. This is the cosine of the argument x squared, while this is the cos squared of the argument x, which could be written like this, cos of x squared. And so to differentiate, we'll go 2 times all of this to the 1 times the derivative in there. 2 times cos x to the 1 times the derivative of cos, which is negative sine. And this tidies up to -2 sine x cos x. And some people write this as negative sine 2x, because we know from previous grades that 2 sine x cos x is sine 2x. Let's differentiate this one. The sine of a complex argument. The derivative will be the cos of that same argument multiplied by the derivative of the argument, 3x squared minus 10x. And I used square brackets here so that one can tell visually where the argument ends and where the factor begins. I like to tidy it up with the factors out front, because now it's clear that the argument obviously must end here. Remember, the argument is the expression that we are taking the cosine of. It's answering the question, cos of what? Oh, the cos of x cubed minus 5x squared. So the argument is x cubed minus 5x squared. Let's continue and differentiate an exponential function that has some trig in it. Recalling how to do this, we make a copy times the ln of the base times the derivative of the exponent. One just has to remember that. Make a copy times the ln of the base times the derivative of the exponent. This says plus 2 sine x because when you differentiate cos, it becomes negative sine, and a negative times this negative is a plus 2 sine x. Continuing, find the equation of the tangent to the function y equals x cos 2x at the point where x equals pi over 2. Solution: perform the usual procedure to answer this question. It's the equation of the tangent to a curve. So we'll have to differentiate a product, first thing prime times the second thing plus the second thing primed, which is minus sine of the same argument times 2, so minus 2 sine 2x times the first thing x. We're interested in the slope, so let's take the x value at the point of tangency and sub it into the derivative and do the math. Of course, we're going to take y prime of pi over 2 and put it in right here, and the 2's cancel, and we get cos of pi. Put it in here, and we get pi, because it's 2 times pi over 2, so pi, and sine of 2 times pi over 2, which is pi, and cos of pi we know. That's negative 1, and sine of pi we know, that's 0. So this is simply negative 1. The slope of this tangent is negative 1. We'll be interested in the y value when x equals pi over 2, so we'll take pi over 2 and plug it into the original to get the y value when x equals pi over 2. So y of pi over 2 equals, subbing in pi over 2 here, pi over 2 times cos of 2x, so 2 times pi over 2, which is just pi, and cos of pi we know to be negative 1. How do we know the cos is negative 1 at pi? Because we're familiar with the cos curve. And the cos curve says that when x is pi, the cos of pi is negative 1. And so this becomes negative pi over 2. We also use this fact right here. We're referencing the cos curve. One should know the cos curve. One should certainly know the cos of pi just by thinking of the cos curve. It's from previous grades of math. And so we have our y value, we have our slope, we have our x value. We can now plug into y equals mx plus b. Here's y equals m, we figured out. X is pi over 2 plus b. Doing the math here, b turns out to be 0, and we have the equation of the tangent to the curve at the point. Y equals negative x. Now I've graphed the curve, and I've also graphed the tangent. Let's take a look at how these things appear on the software. The red line is y equals x cos 2x. Y equals x cos 2x. The red line. There's the point right there where x equals pi over 2, or 180 over 2 if you prefer. There's the point of tangency. This is the line y equals negative x, and you can see that it is tangent at the point where x equals pi over 2. Consider this red line. Now, wouldn't that be fun to graph? Look at all those max and min points and points of inflection and x-intercepts. A nice, fun, enjoyable project. Graph the curve x times cos of 2x using the sketching algorithm. Lots of fun, but I don't have time for it just now. Moving on, Determine the max and the min values of a function on an interval. X is in the interval between 0 and 2 pi. Solution. Perform the max-min algorithm, which is differentiate cos squared x. We did this about 5 minutes ago. It's 2 times cos x to the 1 times the derivative of cos, which is negative sine, which could be written negative sine 2x, we discovered. And so setting this equal to 0, because we're priming it, zeroing it, and solving it, so we've differentiated and set the derivative equal to 0, which means that sine 2x must equal 0. And so that means that 2x must equal 0 or pi or 2 pi, because these are the places where the sine of an argument equals 0. Referencing the sine curve from previous years of math, the sine has x-intercepts at 0, at pi, at 2 pi, at 3 pi, at all the multiples of pi. Now you'll notice that I rolled these all the way out to 4 pi, even though the x has to be in the interval between 0 and 2 pi. What's happening is this says 2x, so we had to multiply both of these numbers by 2. So I rolled it all the way out to 4 pi, so that when I divide through by 2, I get them all. These are the results of setting the derivative of equal to 0, and so according to the algorithm, we're supposed to evaluate y at the critical numbers and the boundaries. Well, 2 of these critical numbers are in fact boundaries. So let's evaluate them all. F of 0, we'll start with the first one, plug it in here. Cos of 0, we know from the curve, is 1. 1 squared is 1, and so we have that one. Similarly for f of pi over 2, cos of pi over 2, referencing the curve, we know that's 0. F of pi, we know that's negative 1, but squared, because we're squaring cosine, is 1. F of 3 pi over 2, referencing the curve, the cosine of 3 pi over 2 is 0. And finally, the cosine of 2 pi is 1, and 1 squared is, again, 1. And so we can see our maxes and our mins here. We've got multiple absolute maximums and multiple absolute minimums. We have a max, then a min, then a max, then a min, then a max.